Good morning to all of you. I am Devendra Kumar Patel from VIT Vellore, India. I welcome you all in this session of hands-on computational fluid dynamics. Here in the present session, we are going to learn the meshing using snappyHexMesh, setting up the problem using OpenFOAM, and post-processing of the data using ParaView. For the present exercise, we have considered the case of impinging slot jet. Here I am having an schematic diagram of the impinging slot jet. As shown in figure, we can see the slot jet which is coming from the nozzle. The shape, this is a nozzle, and the length of the nozzle is small l, and width of the nozzle is capital L. From the nozzle exit, the jet is coming at uniform velocity, that is V naught, and it is impinging to the flat plate at exactly at the location 0, 0. The left boundary and the right boundary and the top boundary are far away from the impingement region. Actually, the region where the jet impinges onto the plate is known as impingement region. We are keeping the left boundary, right boundary and the top boundary far away from the computational domain so that there won't be any error which will propagate from the boundaries will affect the impingement region. Here I like to show you the three-dimensional schematic diagram of the same problem so that the computational domain will be more clear to all of us. This is the three-dimensional computational domain which we are going to consider for the study. Here you can see we are having a slot jet. Okay, we are having three dimensions like x direction toward right, okay, and y direction is vertical and z direction is perpendicular to the screen. Here we have considered a slot jet. Slot jet means the width of the jet which I am showing here. It is not changing when I am moving in the z direction. And the slot jet case is a kind of three-dimensional jet. So the flow field which when the fluid will come from the slot jet will have three-dimensional characteristics. So it is required to have three-dimensional computation for that. That's why we have considered a three-dimensional computational domain. Here, as shown in the figure, the slot jet impinging to the flat plate at an angle of phi. Okay, it is not impinging vertically. We are keeping the inclination of slot jet, and we are having the right fluid boundary far away, that is around 20 W, means it is 20 times of the width of the nozzle. In the same way, the left boundary also 20 W from the location of impingement. The location of impingement is what? That is 0, 0, where the impingement will happen. Okay, and the top boundary, again it is so far from the impingement location, that is 30 W, and width of the computational domain in the z direction, that is 5 W, as shown in the figure. Here you can see. For the computation, we are keeping the left, right and top boundary open. Open means the fluid can enter into the domain and can go out from the domain from these three boundaries, left, right and the top. Here we are considering a submerged jet. That means the atmospheric fluid and the fluid which is coming from the nozzle both are same. Like if we are doing experiment for the air, the atmospheric air is all over, like from the left, from the top, and from the right, the air can come and can out. Okay, and the air is coming from the jet exit. If it is the case of water, then the same fluid will enter from the left, right, and the top boundary. The bottom boundary, yes, it is a solid wall where the jet is impinging. So the fluid from the bottom boundary cannot enter into the domain. In the same way, the wall of the jet, that is the curved shape which you are able to see, curved shape, that is the wall of jet. So here also the fluid cannot enter and cannot go out. Okay, we are keeping this kind of some profile. Why we are considering this kind of profile? So that when the air will come from the top, the fluid will come from the top, it won't have much disturbance because of the shape of the nozzle. That's why we are considering the shape of the nozzle as elliptical shape, so that a smoothness will be there for the incoming fluid which is coming from the top boundary toward the plate. That fluid will come because of the entrainment process. There is no like fan or something blower is blowing the air from the top. It is not like that. Because of the flow of impinging jet close to the wall, it pulls the air from the top, which is known as entrainment process. The first step in the CFD is what we need to generate meshing where the computational will be done. So we have to create a computational domain and then we have to mesh it for the simulation. To create the computational domain, we have first created the surfaces, that is for nozzle wall, nozzle front and back, nozzle exit. Okay, as shown in this figure, we have created the surfaces like nozzle wall. This is the curved surface I am considering as nozzle wall. This is the front surface of the nozzle, which is again a wall. Back surface of the nozzle, that is again a wall. Okay, and there is one more surface which is considering as nozzle exit. We can say nozzle exit, or we can say inlet to the computational domain, because from there the fluid is entering into the domain. And then we are considering, we have made one more surface that will represent the bottom surface and will be considered as wall where the jet is impinging. But the three other faces, that is left, right and top boundary, they are open. So we have not made any surface, we have not created any surface, because it is not required to create that will be created in the snappyHexMesh process. We need the solid surfaces only to make mesh, to generate mesh using snappyHexMesh. I want to show you those faces which I have generated. So here we have made all the STL file. STL file is what? It will represent the surface. It is the basic file format through which we can represent any surface. So I have made 3-4 STL files to represent the jet accurately and the bottom plate accurately. This all STL files we can visualize using ParaView, or there are many other software, but I use ParaView. So here I am opening the ParaView and I want to show you what we have made in this STL file. So just I am calling the back STL. Okay, and that I am representing here. You can see this is a back STL. Okay, So this surface is representing the back surface of the jet. In the same way, I have made the front STL. You can see here, this is the front STL. So back and front STL, these surfaces we have made some using some different software like Salome. I have used Salome software, that is very good, but we can use other software also like AutoCAD, CATIA, SolidWorks. There are many softwares available to make the surfaces, and we need to save those surfaces in STL file. That is the requirement of snappyHexMesh. And then here what we need the exit of the jet. Okay, that one more surface is required, so that also we have made, and here you can see this is the exit of the jet we have made. This is the exit, this one. And now one more curved surface is required, which will be considered as the nozzle wall, right? So here you can see there is a jet wall, okay, nozzle wall, okay, you can give any name, there is no problem. So here this is a nozzle wall. So how many surfaces we have made? 1 2 3 4 4 surfaces we have made to present the jet. Okay, when we will make this jet, we have to be careful about the dimensions. Like here I have considered a unit width of the slot, unit width of the slot jet, and the length of the nozzle is 3 times of the slot width. Thereafter we have considered one more surface which will represent the impingement surface. You can see here, this is the impingement surface, right? And when we are going to make this, we have to be careful about the locations. Like I want to show you the locations wherever you want. It is based on the, like here, if I here we have given the distance of this nozzle exit from the impingement location is 4 times is 5 times of the nozzle width. Okay, so while making the STL file, we have to be careful about the dimensions, at which distance I have to make the nozzle, at which location, how much we have to turn the nozzle. This all we have to decide initially, then only we have to create the surfaces, and after creating the surfaces we have to write the files in STL format as I have shown here. Now further step is what? We are going to merge this all STL file in one STL file. So here I have made a combined STL file, and I am giving the name as domain.stl, and this comprises all the back surface, front surface, inlet, jet wall, plate, all these surfaces, all these STL codes, which is, you can see for the plate, this is the code. This is representing the surface, bottom surface. I have just copied this data to my domain, okay, to my domain STL. So I have copied, and while copying I have to write these things like solid front. Okay, I have copied the data from the front STL. You can see this is the front STL. Okay, so just I have copied like this, Control C, and I have copied here. But when I copied, I have to write this is front. This is representing, this data is representing the front surface of the jet. So that's why I am writing here front. Okay, this is important. We have to write, we have to give some name. When I will copy the another thing like inlet, then I have to copy this and I have to write this inlet. This data will represent the inlet of the jet. So like this we have to write the name. It is important, okay, because these names will be reflected when I am going to give the boundary condition, when I will set up the case in OpenFOAM. So these names are important wherever you want to give any boundary condition, like something surface as treated as wall or inlet or outlet or whatever. So we have to give the names so that that will be called while setting up the problem, and we can give appropriate boundary condition in those locations. So we have given all the names and we have made a combined STL file as shown here. For now I want to load this combined STL file and I want to check whether the everything came or not. So just I am deleting all the previous loaded data. Here I am just resetting it. So I have resetted the session, there is no data loaded. Now I am going to load the domain STL just to cross verify whether we are getting all the surfaces or not. Now you see I have loaded only one combined STL file and everything is coming inside this STL file, and you can see the colors are representing, they are having different name. Like this color is having different name, blue color is having different name, red is different name. You can see the inlet is also different color, that means it is having different name in the STL file. So when we will set up the case in the OpenFOAM, these names will be very important. So after combining all the STL file, we are having domain STL. Now to mesh this, to make the mesh for our required computation, we are going to use snappyHexMesh utility, which is given in the OpenFOAM. So what I have done here, I came to the location where I have installed the OpenFOAM. Here the different versions of OpenFOAM are installed in my laptop. I am planning to use the OpenFOAM 1712. So inside the 1712 there is a tutorial, okay, and from this tutorial I have to copy a particular snappyHexMesh tutorial, okay. So I have copied this motorbike tutorial, okay, and which I have copied to my working folder, okay, that is HOS. HOS is my working folder where I am going to make mesh for the present problem. So this is the same copied folder, and here now I have to modify this as per my requirement. In this copy, in this folder, we will have basically basically two only, I should say two, this is not required even. So basically we'll have two directories, one is constant directory, another is system directory. When you will open, there are so many files in the system directory, but not all are not necessary. The most important files are the surface feature extract and snappyHexMesh and the block mesh, okay. These files are necessary, only three for our snappyHexMesh, okay. Others are necessary for the computation, that we will discuss later. So which is necessary presently, that only we are going to discuss. Thereafter we will see the other files also. So here block mesh, snappyHexMesh, surface feature extract, these files are important, that we'll discuss. Thereafter one more directory we are having, that is a constant directory, and here in the constant directory a very important folder, that is a try surface, okay. So inside the try surface actually we have to paste our domain STL which we have made, okay. So I am pasting here, I am replacing the domain STL with my domain STL which I have made using Salome. Further I have to come back to this folder, okay. This is my main folder where constant and system directory is there. So from here I have to give the commands, so I have to be in this directory. So that's why I am opening the terminal in this directory. You can read where I am, work HOS mesh generation. This is my directory, which is actually this one. Okay, because I am working in the version OpenFOAM 1712, so I have to create the environment so that the commands which is for OpenFOAM 1712 will be executed. So just I am calling the environment, that is 1712, and I have called that environment. Now I am ready to give the different command which is required for meshing. Okay, so here first I want to show you the domain in the ParaView which is available till now. So what I'm doing, I'm going and I'm opening the ParaView at the same location, and I know I have pasted my domain STL inside the constant directory and inside the try surface, and opening the domain STL like this. Okay, so this is the STL file which I have pasted. Now our plan is what? Our plan, we have to actually make one left boundary here, top boundary here, and right boundary here, so that a complete computational domain will be made. Actually presently we are not having the front, the back, the top, and the right and the left fluid boundaries, so which I have to make, and I have to keep this surface inside to that computational domain, and then we have to mesh. Okay, so who will create that? So for that, there I'm going to use the block mesh technique. Okay, so here you can see I'm having a block mesh file. Okay, just first I want to run this block mesh, whatever we are having here, and then I will show you what the different values I am going to change, and which will cover my geometry inside that domain. So I want to run the block mesh first. Okay, so I will come back to the terminal, which is in the right location. Okay, which is in this folder. So I am going to run block mesh. Okay, so this is the command to run the block mesh in OpenFOAM 1712. So the block mesh, actually what it is happening, based on the information which is in this directory, that is the block mesh dictionary. Inside this directory we are having some information. Based on that we have created some mesh. Now I want to see that mesh, which kind of meshes we have created. So here I am again opening the ParaView at the same location, and I want to call the mesh which I have presently made using block mesh. You can see I have created the block mesh. Okay, and using block mesh I got this kind of mesh. Here you can see the important thing is what? It is three-dimensional. If I'll see, the three-dimensional width is very less. This is in X direction, this is in Y direction. Okay, but in Z direction you can see in Z direction we are having only one grid point, and it is very thin also. So it is not a three-dimensional mesh. Okay, which is created by the block mesh. I need three-dimensional, that we'll do later. First we'll make two-dimensional, and that we will extrude in the Z direction to have three-dimensional mesh. Okay, to know where, if I will call my STL file here, I will come to know that whether this mesh is sufficient large to consider my STL file inside this mesh. That I have to check. So that's why I am calling our domain STL, and I am checking here whether the mesh will able to consider my STL file inside it. So what I have seen, there is my mesh which I have generated through block mesh, it is very small. So actually I have to make it large, right? So I have to make it large, this. So for that I have to edit the block mesh first. Okay, and how I'll edit, I will try to make the block mesh I will try to change the parameters so that the block mesh will be sufficient big and it will able to create left, right, top, front and back surfaces. Okay, so let us see the block mesh file, what are the things we need to change. Here is the block mesh dictionary which is inside the system folder, and when I'm opening we can see there are some coordinates. Okay, there is how many coordinate? Total 8 number of coordinate. Okay, actually this is the coordinate through which the block mesh is generated, and it has created a rectangular kind of shape in 3 dimension. Okay, a box kind of shape. So actually these are the 8 coordinates of the box under which the block mesh has generated. Okay, just these are here. I want to close this one. You see, actually this is the 1 2 3 4 for the front and 4 for the back. So the 8 coordinates they have written in the block mesh to create a box kind of geometry. Now that we have to edit. When we'll edit it, we can make this block mesh bigger. Okay, for example, for the first test I want to increase the depth in the Z direction, just to show you. Okay, so what we have to do, we have to see which is going to affect the Z direction. It is very simple. You can see this is the X coordinate, this is the Y coordinate, this is the Z coordinate. For 8 different vertices of the box, we are having 8 points. Okay, and you can see the Z coordinate carefully. If you'll see, the Z coordinate for the back face is located at minus 0.0025, and the front coordinate, you can see this is all the front. These all 4 points are in the front, and these all 4 points are at the back. So if I will change the value, that is minus 0.0025, okay, then I can increase the depth of the box. Okay, so that I'm going to do. You see how. So just I'm changing it. Okay, making little longer in the Z direction. Okay, both side. Okay, I have saved it. So now again we have to make the block mesh, then only the mesh will be generated. So I'm running the block mesh command one more time, and now I want to see what has been generated. Okay, so I'm coming here and I'm refreshing it. Okay, refresh it and check what has happened. So here if you'll see in the 3 dimension, this is the 3-dimensional view, and if I will turn like this, you will able to see what has happened in the Z direction also. You can see this is our Z direction. Okay, so in the Z direction the domain has been increased, right? So what is needed, actually what we are looking for, I have to increase the height in the X direction, okay, in the Y direction and in the X direction, so that my STL file will be completely covered by the domain, covered by the computational domain. So here actually we have to edit these points, okay, which is going to make a rectangular box which will be considered as our computational domain, and this will cover this will enclose the geometry which we have made in the STL file. And I have now already changed the values of these coordinates. okay, how we change, how we judge the values, and how we consider that we can discuss in later, but this I have changed for time being. And then I have given the number of mesh which is required in X, which is required in Y direction. Okay, so this much only we have, this much values only I have changed. So now again I am running the block mesh, okay, and after running the block mesh, again I want to refresh the geometry, and I'll see which kind of block mesh has been generated. Okay, so this is done by block mesh only. Here we can see now we are having a sufficient length of the block mesh in the X direction, in the Y direction, and in the Z direction. Okay, this length we can change by changing the values in the block mesh dictionary. Okay, and the location also, location of this box we can shift by changing the coordinates. Okay, and how many number of meshes we have made in the X direction, that is 40, and in the Y direction, that is 30. This all I have mentioned randomly. Okay, and one more thing, because as I told you, here we are planning to make a two-dimensional mesh first, then we are going to change that two-dimensional mesh by extruding one face of the two-dimensional mesh in Z direction to have three-dimensional mesh. Okay, so as I am going to make two-dimensional mesh, so for that what the width presently I have chosen here, you can see this is the width I have chosen, which is completely considering the STL file inside the computational domain, is not okay. Actually I am going to make two-dimensional mesh, so I can make this width little lesser, much lesser. Okay, I can make this width much lesser. So that I am going to do here now. How I am going to make the much lesser width by taking the points. I want to show you here. You see the 4 point are making the front face and the 4 point are making the back face. So I have to keep closer these 4 points, okay, in the Z direction, so I can make the thin mesh. I can make thin block mesh. Okay, so that I want to do. So here you can see I have changed the values of Z, and I am trying to make all the 8 points, 4 point for the front face and 4 point for the back face, close to each other. Okay, and after changing this, I want to run the block mesh again in order to make the mesh. Okay, after making the mesh, we can see what is happening here. Now I want to update it. Whatever new mesh has been made, I want to update. You can see this has gone closer, right? Front face and the back face, they become closer to each other. I want to make some more. Okay, so again I am going to reduce the values. Okay, so I am reducing like this. Just I am putting one more 0 values. Okay, because first I have to make the two-dimensional mesh. That's why I am doing all those things. Okay, so you can check here. Again I have to run the block mesh. Okay, so block mesh command is here. Now it is done. We can refresh it and we can check. Now it is came very closer. Okay, because we are going to make two-dimensional mesh, right? It is too close to each other, and it is okay. And actually one more requirement we need, that I want to inform you. When we are going to do a snappyHexMesh, the first requirement is what? These meshes which you are able to see, if I'll show you in the two-dimension situation, you can see here, these each cell should be cubic kind of. Okay, which is not here. It is clearly visible, these cells are not like cube. Okay, and you can see, if I'll see from the side here also, these length are very small, very small. It is not making a cube. So I have to keep in mind that when I'm going for snappyHexMesh, then these each cell should be kind of cube, then only we are going to get a good snappyHexMesh results. So for that, again what we have to do, we have to change the number of grid points in x direction, number of grid point in y direction, and so that we will have a cube kind of cells which is made by block mesh. So in order to have cube mesh all over the domain, I have changed the number of grid point in x and number of grid point in y, and I have also adjusted the depth in the z direction. So after doing that, again I have run that command block mesh, and when block mesh completed, I plotted the block mesh again, and you can see here I am getting now cube kind of meshes. This is okay. So it is exactly cube in x and y, one thing. Another thing, it is exactly cube in the z also. Okay, you can see this is just it is cube in z also. So if we are making this kind of mesh first, okay, then it will produce a good snappyHexMesh. You can say it is the requirement of snappyHexMesh also. The work is not completed yet. If you'll see this mesh, which is very coarse mesh for this kind of simulation, actually we need some dense mesh close to the exit of a nozzle, and some dense mesh close to the surfaces to capture the boundary layer phenomena over the wall, and also we need some dense mesh over this flat surface where the jet is impinging to capture the boundary layer phenomena. Okay, one more thing I want to say, if I am just hiding this jet, you can see what is happening. So I don't need the mesh which is inside, which is coming inside of this jet, okay, inside this wall. I have to remove those meshes, and I have to create very fine meshes close to the wall of nozzle, close to the exit of nozzle, and also I have to create some dense meshes close to the impingement surface. So for that, now we have to go for snappyHexMesh. Till now we have done the block mesh, that is a primary mesh made by block mesh, which will be corrected by the snappyHexMesh to have a fine and good mesh as per the requirement, as per the geometry. In order to remove the meshes which is actually coming inside of this geometry, okay, like when I'm hiding, you can see some meshes are coming inside the geometry. It is not required because we are not going to do any simulation inside that. So we have to remove this geometry, remove this meshes which is coming inside the geometry, for which we are coming to the next step. The next step is what? The surface feature extract. This is what we will see. This a very small code is inside the surface feature extract directory. Directory means file. It is written just include angle 150, means what? It will consider when I am going to extract the features of the surfaces, which is in the domain. When I made the domain, I have made many surfaces. So when I will extract the features of those surfaces, if the angle will be if the angle, cutting angle will be higher than 150, lower than 150, then it will be considered as a edge. That's it, nothing else. So here I am going to run this surface feature extract. By default value is 150, 130 in some cases. Okay, we will discuss about this value later in detail. We can run this command to extract the surface feature, and what will happen we will see here. So here now to show you what is going on, I am just deleting these files. Okay, and I want to delete. Okay, there is no other file. Okay, so when I will run the surface feature extract, actually surface feature extract is going to read the STL file which we have pasted inside the tri-surface directory, and it will extract the surface features and it will make a new file. Okay, just for example, I am running this surface feature extract. This is another utility which will extract the surface feature. So in OpenFOAM 1712 we write like this to run the run the command which is inside this system directory, that is here. Okay, surface feature extract. Okay, so I'm going to run it. Surface feature extract, extract, like this. Okay, I'm running it, and after running you can see what happened. So when I will open to this constant directory, you can see this I deleted that, and when I given the command surface feature extract, this file has generated and it has extracted the surface from the domain file, domain STL file, and also it has made one more new file, domain.stl, inside the tri-surfaces. Okay, now we have to run the snappyHexMesh. Okay, so snappyHexMesh, it is a little long file. You can see here long codes are there inside the snappyHexMesh, and when I'm going to run this code, we have to be careful about the three sections. Okay, the three sections are like this. So first is what? Castled mesh. Okay, castled mesh, one operation will be castled mesh, the another will be snap, and third will be add layer. Okay, so in 3 steps it is going to do the operation. In castled mesh, it will remove the meshes which is coming inside the nozzle. Okay, and then in the snap, the surfaces will be snapped to the grid accurately, and curved surface we are going to get, and add layer, it will make the layer over the wall. Where we want to make the layers like boundary layers, it will make those layers close to the required surfaces. One by one we'll see. I have to edit this file, and the edited file I will run, and I will show you what are the things are happening. So here we are having 3 steps. So one by one we will see what is happening in each step. So first I want to run the block mesh, and which we have already run, but again I am running the same. Okay, the block mesh. So when I have completed the block mesh command, and when I want to see what happens, so what we got, we have already discussed about this. We got a simple cubic kind of mesh structure, and which is actually making the full computational domain. If I want to if I want to call this domain STL, you can see domain STL is coming here, and plate is also there. We are having both the plate you can see plate is here, and the nozzle is here. Okay, now the block mesh has generated a simple mesh, but it is not taking care. I do not need the meshes in the region where I am having nozzle, and also I have to cut some meshes which is coming below the plate. You can see here below the plate also we are having some meshes that I want to cut. Okay, I need the meshes above the plate and outside of this nozzle. So the first step is what we have to cut this meshes which is not required. So after this we have run one command, that is surface feature extract, to extract the features of surfaces which we have made in the domain STL. After that, the first step you can see I have written here true. Okay, means here in this step we are going to read the features of surfaces. Based on that, we are going to cut the meshes which is not required. Okay, so I don't want to do the second step, that we'll do later, so I'm writing false like this, and here also I'm writing false. Okay, so when I will run this snappyHexMesh command, it is going to remove the meshes where it is not required. So here you see some small things which I want to tell you, but we will discuss this detail when the session will be started later. So here I am calling what? I am calling which is required surface. Using that I want to cut the meshes, like inlet from the STL file, which surface is necessary to cut down the meshes. Jet wall is necessary, plate is necessary, so I have called those surfaces here. Here some values are there, so these values we will discuss later how it is affecting. And then I am coming further down, and one more thing important I am giving, when I will cut the meshes. Okay, when I will cut the meshes near to the inlet, near to the jet wall, and near to the plate, I will increase the mesh density. Okay, actually in the block mesh we have created some mesh density which is uniform. You can see it is uniform all over, but close to this surfaces I want to increase the density of mesh to have the good capturing capability of the mesh. Okay, so I want to run this command, and you can see from here to this is the last bracket. From here to there, this one is responsible for the first step, castelled mesh control, right? So I am running this command, snappyHexMesh, snappyHexMesh. So when I will run this command, out of these three, only the first step will be done. Okay, and when the first step will be done, one more directory will be created with the new meshes. Okay, for example, just I'm saving this what I have done. Okay, and I'm running this command, and we'll see one more directory will be created. So see, one more directory has been created here. Okay, and now I want to update my mesh. What happens? Okay, so to update it, I will come to the plot and I will refresh and I will update. When I update, I will able to see what I have increased the density close to the surfaces, right, and close to the plate. And one more thing, when I will close this one, you see the jet is not inside the jet, there is no meshes. Okay, but the problem is what you see, we are not having the surface, the curved surface I am not getting. Okay, curved surface and here will be a straight surface. It is not coming. So at the bottom what happened, the plate is already, it was a flat, so there was no problem and we got the correct mesh close to the plate. But close to the curved surface and inclined surface we are having the problem. That can be removed, okay, and it will be removed in the second step. Okay, so I am just cancelling the first step because I have already done. Okay, now I am making the second step true. Okay, so what it will do, it will snap. Okay, it will snap. Snap is the next operation. So in the snap it will, what it will do, there is a special curved surface we have used, an inclined surface we have used for the jet, that will be exactly snapped to the mesh. Okay, so that snap controls, whatever snap controls we use by default, these values also we are going to discuss later, what are the different values which we are providing here. Snap control I have little bit modified. Okay, so these values we are going to discuss detail later. So this operation is going to complete and we'll see what will happen. So I am running again the snappyHexMesh command, but this time when I will run, because the first section is false and the last section is false, only snap will work. So when I will run the snappyHexMesh command, the snap will run. Okay, and you can see here some iteration is going on to fit the curved surfaces nicely. So it has taken the geometry, taken the first mesh which is like this. Okay, this meshes it has taken and it will try to snap accurately whatever surface we are having. Now we will see how the second mesh I got. See, so now we are able to see the accurate curved surface which I was created for our geometry of nozzle. In the same way here there is no problem, you can see we got the good thing. Okay, now the next aim is what, we have to create some boundary layer here so that we will get an accurate prediction of boundary layer flow field. Okay, so for that, in the snappyHexMesh itself we are going to do the third operation, that is, so I have to close this one. I am writing false, okay, and here I will write true. If I will run snappyHexMesh command again, then if I will run snappyHexMesh command again, the first operation and the second operation will not be done. The third operation, that is add layer, will be done. Now in the add layer control we are having again some bunch of commands, and in the add layer you can see I have given, I want the layers, boundary layers grid over the jet wall and the plate. That's why I have written 5 for plate and jet wall. Wherever you want that we can write here, but till now it is sufficient. That's why we are writing this and we'll proceed with that. So what we have to do to make the layers, now if I'll run the snappyHexMesh command, it will take the second grid which we got after mesh operation, after snap operation, that will be taken and the layers will be added. So I am running the snappyHexMesh command again, and this is iterating and putting the boundary layers. You can see there is one important information we'll have here. Let us see. Just 1 minute. Okay, so that important information is what, here you can see over the jet wall, over the plate, we are getting 100% accuracy. So they have made the layers over the plate and over the jet wall nicely, that we can see here also. This we got from the second step, and in the third step we got another mesh that is at 0.003. So I have to refresh it and then I have to load it. Now you can see we got a very good nice boundary layer over the jet surface. jet wall surface. In the same way we will get because here also we needed, so here also we got very good mesh close to the jet wall. Okay, now what are the different surfaces made by this operation? This all is written here. You can see this is a poly mesh. Okay, poly mesh, and here inside that you can see front, back, inlet, outlet, okay, left, right, jet wall. That we have to see carefully, because some, like this outlet, I have not given which is this face. I will see that, and I can edit here also. Okay, I can change the name of the boundary here also. Okay, now after that what we have to do, what we have done till now, we have just made a two-dimensional very good mesh here. Okay, it is a two-dimensional, and then what we need, we want to extrude this mesh in our z direction. Okay, and we'll keep some more number of grid points so that it will be like a three-dimensional excellent mesh. Okay, here one more thing I want to inform. When I was editing this snappyHexMesh dictionary, I was doing step by step. This all we can do in one command also. So if I'll make like true for all, okay, TRUE, true for all, true for all. Okay, so in one command, that is snappyHexMesh command, all the three steps will be executed, and it will make a very good mesh directly. Okay, and here I want to run all together, and I don't want to make so many folders like this. Okay, whatever will be done one by, it will overwrite. Okay, so that's why I'm not interested to make many folders. I'm deleting this all, and this all will be created, it will overwrite, and it will create the snappyHexMesh in one file only, in one folder only. So first I'm running the block mesh, then I'm running the surface feature extract, then I'm running the snappyHexMesh, and I have to write overwrite command also, like this, and it will overwrite all the things. Okay, and there will be only one final file that I am going to use, and that final file will be inside this poly mesh. This is actually our mesh information inside this poly mesh. If I plot this, I will refresh it, and you can see I will get the final mesh in the same way. It is the final mesh. So you can see how nicely we are getting the hex mesh all over cubical kind of mesh, and very close to the curve we are having dense meshes. This kind of meshes are very good for three-dimensional calculation, because it takes lesser time compared to the other meshes, because it is not having any very less very less non-orthogonality. Okay, we can check the our mesh quality also. So here I'll do check mesh. Okay, so check mesh operation will give you the non-orthogonality. They have checked, and they are saying there is very less non-orthogonality, and this mesh is good. Okay, here you can see the non-orthogonality maximum is 48, and minimum is, that average is 6.0 something. So all over we will say this mesh is excellent. And now our aim is what? I will take the front face of this mesh. I will take the front face of this mesh, and I will extrude in the z direction to have the meshes in the third direction, that is in the z direction. Whatever number of meshes I want, that I will put there, and I will extrude the front face of the mesh. The extrude operation we do in the other folder. Here I have written one more folder. This is the mesh generation, where we have made the snappyHexMesh two-dimensional, that I am going to extrude to make three-dimensional meshes. So extrude operation I am going to do here. here the same files what I have copied from the OpenFOAM 1712, it is same here, but one new file I have added, that is extrude mesh. So here very important file, that is extrude mesh. So what we are doing here, we are calling the source case. That means it is another folder where we have made the snappyHexMesh. You can see the snappyHexMesh is inside this mesh generation. So we are calling the that folder, and we are considering their mesh whatever inside the poly mesh. From there we are taking the front face, okay, and after taking the front face we are actually extruding in the linear direction, okay, in the Z direction we are extruding. So when we are extruding in the Z direction, what we are doing, we are making 50 number of layers, and we are keeping the thickness between the gap between the each layer, that is 0.02. So this simple command is here, and other things which is written in this, we can make the wedge kind of geometry also. Those things we are going to discuss later. So here I have already fitted, and I want to run this command extrude mesh. First what I have to do, I have to come to this folder, that is extrude mesh. Okay, I came here. Now I have to open the terminal at the same location. I have to give the environment, that is OpenFOAM 1712, and extrude mesh we have to run. So it will take the mesh which I have made in the another folder. From there the front mesh, the mesh at the front face will be taken, and that will be extruded 50 times, and it will keep the gap between the faces 0.02. So let us see which kind of mesh I finally got. Using ParaView I can see the mesh, and I am plotting that mesh. Okay, so you can see in the third direction also I got these many, this is the thickness. Okay, and if I'll put the meshes, let me show like this, more visible. You can see this is the third direction. Okay, the third direction, which kind of meshes I am getting in the third direction. Okay, like this, so many meshes I have created. The gap between the meshes we can keep nicely, so that it will be almost like a cubic kind of mesh. That will be good. I have given some random value, and based on that we have made the mesh. Need to be correct more. Okay, so now you can see which kind of mesh we are having. Very nice mesh, okay, in XY direction. And just if I want to see which kind of mesh I am having over the jet wall and inlet, I can see from here. You can see this is the and front back also we can consider. Okay, over the jet, how, which kind of mesh I am having. Okay, in the Z direction, you see. And now for the full domain, if I want to see, it will look like, just wait, it is internal mesh, it is look like this, it will be like this. So it is an excellent mesh, because we are getting very good structures where which will reduce structures of mesh, which will reduce the computational time. And further, in the next part of the video, we are going to put the boundary condition at the different surfaces. Okay, this is our top surface, this is our right, this is left surface and bottom, and there is a jet wall and jet exit. Everywhere we have to put some boundary condition. We are going to do simulation for incompressible turbulent flow using large-eddy simulation. So in the next class, I will in the next session I will try to explain how we are going to setting up the cases and how we'll simulate in OpenFOAM. I would like to thank you to be patient. It is actually very long discussion. I'll try to make short videos for next sessions. Thank you very much.